Welcome back, researchers and XAI enthusiasts, to the Autumn School 2024 for Interpretability in Deep Learning. After a fascinating recap of the brief history and timeline of AI, let's move forward to Module 1.2 for concept introduction and explore the evolution of AI, focusing specifically in the interpretability perspective in deep learning. Understanding the history of AI has set a solid foundation for grasping the complexities of explainable AI. It is crucial to have this background to appreciate the challenges and advancement in this field. Today, we shall go through the second submodule for the course, tracing the evolution of interpretability and explainability. In research, it is important to understand what has been done before, like demands to extensively review related works while drafting a manuscript. Similarly, we'll understand techniques, taxonomies, demands for interpretability, limitations of existing methods, emerging trends, and future directions in AI explainability. We will also discuss its societal impact and applications. This session will be less technical and more about introducing broader terms and concepts necessary to easily follow up as the course advances in August. Before I proceed with today's lecture, let's start with a quick quiz to get everyone engaged. It's a virtual session, but a bit of interaction may help wake our attention, right? So we start with question 1. Which of the following is a major challenge in achieving interpretability in deep learning models? Is it A. Scalability, B. Data collection, C. Model training time, or D. Hardware requirement? Now, please pause the video for a couple of seconds, think for your answer, and then resume to see if you're correct. Great. Yes, scalability is indeed a significant challenge. As models become larger and more complex, interpreting the factors contributing to their decision making becomes more difficult. Therefore, achieving sustainable and scalable AI is essential to make it more interpretable. Next, do deep learning models with higher accuracy tends to be more interpretable? Is it true or false? Hope you get this correct. Yes, false. Higher accuracy does not imply greater interpretability. This is why we need to focus on making models interpretable at every stage, regardless of their accuracy. Lastly, which of the following is not commonly used technique for interpretability in deep learning models? Is it GradCam, B. Line, C. Dropout, D. SHAP? If you have marked dropout, you are correct again. Dropout is a regularization technique to prevent overfitting in deep learning models and does not contribute to model interpretability. Do not worry, we'll discuss these terms in details later on. Now that we are active, let's discuss what we mean by interpretability. It's a debatable topic with various definitions, but common themes include understanding and reasoning behind a model's decision. In 2019, Miller provided a commonly used non-mathematical definitions that defines interpretability as understanding the reason behind a decision. Keywords here are understand, reason, and decisions. Montavon et al.'s definition aligns with this by emphasizing the transformation of abstract concepts into comprehensible forms. Keywords here are concept and comprehend. We classified popular keywords into three major categories. 1. Vision based on model or data. 2. Algorithmic or methodic insights. And 3. Ethical implications. This attempts to categorize the list into non-exclusive but mutually shared knowledge commonly found in the literature will help us provide a framework for dealing with the concepts of future interpretability statements. Please note that the key aspects of interpretability includes transparency, secureness, trustworthiness, unbiased, fair, accountable, reproducibility, and stability. Let us follow this up with some case scenarios. Consider this. How would you react if a Google mistakenly classified black people as gorilla? Or if a self-driving car failed to recognize a pedestrian? These are only few of many real-world examples highlighting the need for interpretability. In 2018, a CPR study showed how perturbing a stop sign with graffiti could lead to a misclassification as a speed limit sign. The left image shows a real graffiti on a stop sign, something that most humans would not think is suspicious. The right image shows us a physical perturbation applied to a stop sign. They have designed their perturbation to mimic graffiti and thus hide in the human psyche, which led to a misclassification of a stop sign to a speed limit of 45. Such error in autonomous driving can have serious consequences. This brings us to the demand for interpretability in AI system, which is crucial across various fields like healthcare, finance, security, and more. In the context of AI innovation, an application that has entered a new era, interpretability helps us understand and correct this model's decision-making process. In practice, we encounter multiple interpretations across various domains. Users need to comprehend these systems to correct or establish problems accurately. For example, can we trust an AI system for automatic document translations? What benchmarks should we use to evaluate autonomous vehicle safety claims? A user may be interested in the basics of explanation. How do we handle adverse scenarios? Don't you agree that these questions require robust interpretability frameworks? But the question could be, what exactly is interpretability in deep learning? Well, it depends. I'll begin this section with a convincing introduction stating we'll encounter multiple interpretations from diverse research domains. Different stakeholders have different interpretability needs. For companies, transparency might involve sharing internal workings, while for users, it may mean understanding how decisions are made. Doctors, lawyers, and customers each have unique perspective on what is essential for them. Therefore, it is crucial to develop interpretability techniques that cater to diverse requirements. This may include questions like, can a user confirm the privacy assurance of an AI system that I want to use for automatic document translation? Can a regulator track what leads to an autonomous vehicle accident? What benchmarks should we use to evaluate an autonomous car company's safety claim? Can I, as an academic, conduct unbiased research on large-scale AI without industry compute power? As an AI developer, can I confirm that my rivals will not cut corners to gain an edge? Users might need assurance about privacy in AI systems or benchmarks for autonomous vehicle safety. Regulators, academics, and AI developers each have unique perspectives on interpretability. Interpretability of AI or deep learning ensures that models are understandable and reliable, but varies widely based on the target consumer, with no universal or clear consensus at present. Developing a holistic approach to interpretability means considering various factors and building robust systems. This follows a dependency based on the target audience as we proceed further in the development to use timeline that we can see in the image below. In summary, the field is constantly developing and involves balancing accuracy with interpretability and addressing the specific need of various users. No wonder we hear the buzzword explainable quite often. Now, that is why it is important to evaluate the risk associated and the benefits of the justification catered to the target users. Therefore, we need to discuss one major aspect associated with XAI, that is balancing the risk versus the benefit of interpretability. It is important to consider not all model needs to be interpretable. It depends on the application and the impact on human decisions. For example, in high-stake environment like healthcare, interpretability is crucial, while in other areas it might be less critical like movie recommendation or an ad server, where the degree of consequences is low for an unacceptable result. You won't expect strictness in accuracy and its transparency watching a web series recommendation on Netflix, but definitely worry if a credit scoring system has marked your profile as defaulter, while you pay all the bills in time and have been carefully managing your finances. On the other spectrum, there are a lot of problems which are well studied and explored, be it MNIST handwritten digit recognition. But we soon face with the dilemma of incomplete problem formalization in real world application when there is no guided principle to ensure 100% transparency in ethical conducts or safety check for all scenario. Interestingly, Wang et al. In 2015 criticized interpretability versus accuracy. Contrary to the optimism of human-friendly explanation, oversimplification could be a curse in itself. That is, low soundness may demand more mental exercise from the users, resulting in loss of trust in explanation and attention to such explanations. They decided to give up the ability to explain in order to remain maximally accurate. Kulesa et al. In 2013 presented their finding on how completeness overweights soundness. In explanation, led users' mental model to evaluate cost versus benefit trade-off to attend an explanation. So the bigger doubt everyone has, what should we do? I am so confused. I would consider this as explainable AI is a young field but rapidly developing. Two key factors are accepting that human intuition alone is insufficient for understanding complex models, and the continuous development of new methods will help enhance interpretability. So let us look at some of the methods now, since we have the better understanding of the overall need and relevance. With hundreds of different classification regimes that people have followed over time and suits their application, I have tried to consolidate all into one and make things simpler for you. In this nomenclature, we'll classify interpretability methods into two broad categories. One, explaining the internal structure, and second, explaining the model's decision. Internal explanation might involve simplifications of feature relevance, while decision explanations might be post hoc, like saliency map, integrated gradients, or attention mechanism. On the left, you can see the model structure interpretability, which is further subdivided into explaining by simplifications and explaining by feature relevance. Under explaining by simplification, we have the methods like prototypes, distillation, probes, and network dissection. On the right, let's look at some interpretability techniques explaining models' decision. This can be broadly classified into self-explainable white box models, making model interpretable by design, such as using decision trees or logistic regression, rule-based learners, and others. On the other hand of the spectrum are black box models, which depends on subcategories of explanation styles to provide transparency to the decisions. These techniques can be model specific or model agnostic, depending on the needs. Model agnostic methods like LIME, Anchor, and SHAP can be applied to various models, providing insight regardless of its internal structure. These tools help us understand and interpret complex models, making them versatile tool in interpretability toolbox. For instance, Shapley values and LIME help explain model prediction, while integrated gradients and saliency map provides insight into neural networks. We'll dig deeper into the specific methods like LIME, which has become a standard tool for interpretability in the past decade. There is a recent paper that came out that is GLIME, which is also interesting to look further. Other techniques include example-based reasoning like counterfactual explanations, adversarial examples, and influence functions. Lastly, model-specific black box model explanations involve post-hoc analyses like saliency map, integrated gradients, and attention mechanism. Transparency can be achieved through various techniques, such as using saliency map to highlight important features or employing post-hoc analysis to understand model's decision. It is about making complex process comprehensible to different stakeholders. The scope, is it local or global, and the type of problem, classification or regression. This classification helps in selecting the appropriate interpretability technique. I felt this is a good and clear alternative to understand the bigger terminologies and choose the kind of interpretability direction based on the filters for its applications. For example, it is important to understand if it's a classification or a regression problem, or what kind of input and output are we dealing with. Based on that, we can narrow down our search for the method to use. We realized that the lack of genuine agreement on explainability stifles progress in the field. To address this issue, people must first learn the basic taxonomies and definition developed by the AI community for classifying different approaches to interpretations. We shall use these terms often, so it's better to go through this once for all. The taxonomy of interpretability includes understanding the nature of interpretation. Numerous ideas have been proposed that underlies the effectiveness of explanation. These explanations are often sought when there are contrastive or counterintuitive data demanding insights into breaking the biases which might have caused it. Some of these biases introduced could be the following. It could be the selective bias, social bias, or the likelihood biases. The scope of interpretation, that is the local versus global. Local interpretability focuses on instance level explanation, while global interpretability looks at the overall model's behavior. Interestingly, revisiting pieces of literature unanimously suggests researchers' preference for local explanation to interpret the predictions of deep neural networks. Model generalization is the third category, which could be model specific or model agnostic. Different approaches to interpretability, whether model specific or model agnostic, each have their advantages. Model specific methods delve into the internal working, while the model agnostic methods do not and can be applied universally. The generalization strategy we may apply will depend on the category of the model we have trained and the kind of data we are using based on the access to the model's internal mechanism or model independent function based on the input-output data. There is a nice flowchart which describes for the pipeline from the input till the interpretation, and which a surrogate model fitting could be one way of the interpretable model, or you can use the post hoc explanation technique to bypass the black box nature of the AI model and generate explanations for the transparency. Here you would have an interesting consideration of model's generalization capability. A model that is easy to understand may not always be the most accurate, but it can provide valuable insight into the decision making process. For example, a decision tree can clearly show how decisions are made, while a complex neural network may require additional tools to interpret. Next, we have the level of transparency with three principal degrees of openness in ML model: simulability, decomposability, and algorithmic transparency. Transparency involves understanding the model's structure and functioning, while composability focuses on decomposing a model into understandable components. Here, simulatability refers to the capacity of a model to allow a user to understand its structure and functioning entirely. While decomposability breaks down the model into components, the degree to which a model can be decomposed into its individual components, that is, input, parameters, and output, and their intuitive explanations. And algorithmic transparency assesses the model's general behavior, the degree of confidence of a learning algorithm to behave sensibly in general. The image here is a good example where all the three models try to learn from a given input of X weights and the output of Y age prediction. The internal functions can be as complex as shown in 1 or can have a bit of transparency as we can see in 2. On the first case, it's hard to compute intuitively in your mind and get what's going behind the hood. While in third case, it gets more easier and easy to communicate between users, that if 90% of the data have X greater than 180, then we can apply rule A, or if 85% of training data have X plus Y greater than 150, we can apply rule B. So these are three different ways in which a model can be trained and have a different kind of interpretability. And this level of transparency will help user attain their goal. Last but not the least, we have the model of black box inspection. Basically refers to the mode in which a method generates explanations. Explaining models before they are fully trained, that is an anti-hoc setting, or after they have produced result, a post-hoc setting, involves different strategies. Anti-hoc explanation can help in designing transparent models from the start, while post-hoc explanations are essential for understanding already complex models. Picture of interest would be, are we going for a model based interpretability or we are going for post-hoc interpretability? What I mean with this is, while interpretable design reveals the internal working of the model with the use of surrogate model to explain its method broadly, post-hoc interpretation attempts to justify the behavior of a black box model by poking the model from outside for validation. That is, for a black box model, we have no impact on the predictive accuracy of the model, but we definitely have an increase in the descriptive accuracy. We don't have any effect on predictive accuracy because we don't interfere or perturb the model during its learning, but we try to perturb the model after it has been learned and in place. For example, of using the feature relevance, saliency analysis, or network visualization, where we try to perturb the input-output relationship of a model that has been learned to understand what part of the model or which neuron, or for example which pixel for an image has an importance for a particular classification of, say, cat or a fish. Or we try to dissect a network's layer to understand what are the maximized activations for a particular image of input to produce a particular classification output. On the other spectrum, we have the white or the gray box model, in which we have, say, a 2 or 3 layer decision trees, k nearest neighbor, or rules which are inherently explainable by itself. The grayness of the model depends on the level of transparency or the degree of transparency in use. So a 3-layer decision tree may be very close to a white box model, where when you try to train the model, you can intuitively understand what it has actually learned to produce a particular decision. But when we increase the layer for a decision tree to, say, 20 layers, or a rule-based system in which we have, like, say, 20 rules, there is a chance that we can understand what rules were triggered during the learning process, but it gets a little counterintuitive to clearly state what has the model learned to make a particular decision, and that makes it an area of gray boxes. We'll explore different methods and their application throughout the course. Understanding these techniques will help you choose the right approach for a specific need. But here I believe you would have one question in mind. What about explainability versus interpretability? Explainability and interpretability are often used interchangeably but have distinct meanings. Explainability refers to the clarity of a decision-making process, while interpretability is about making the models working understandable to humans. Explainability can be complex and may require expert guidance, whereas interpretability aims to simplify the model for a broader understanding. Both are essential for developing robust and transparent AI system. And for instance, a decision tree is inherently interpretable because it uses clear rules. This model uses simple mathematical principles that are easy to understand for any user level. In contrast, as problems become more complex, we need more sophisticated interpretability techniques. Neural networks often require post hoc methods like saliency maps or line to explain their decision. The choice between explainability and interpretability depend on the context and user requirement. Both explainable and interpretable approaches aims to make AI model more understandable. The goal is to bridge the gap between complex model output and human understanding, ensuring that AI systems are both reliable and transparent. To just summarize it in simple terms once again, for example, if we take a linear regression, it is more interpretable in a direction that you can understand with the heat map, like which input feature has a correlation with the other input features for a particular prediction. Whereas if we use CNN models, the activation map is explainable, but then it might need specific human proficiency to understand what it has actually learned. It's not easy for layman to understand it easily, and that's where we have a little slight boundary between interpretable and explainable definition, but it is often used interchangeably, so you don't have to worry a lot between these terminologies. Lastly, we have another way of classification based on the need of interpretability in three latent dimensions, that is data driven, task driven, and model driven. Subcategories here reflect factors relevant to a latent dimension based on the current objectives. This analysis is a first step towards establishing key concepts in the context of laws governing AI models and procedures, like through the GDPR. For example, in the data-driven, there are uncertainties whether epistemic or aleatory influences the data. Another consideration is the stochasticity, be it the continuous or discrete nature of the training data. For task-driven interpretability, we should consider the problem scope, time constraint, user expertise, and incompleteness severity as previously discussed. Lastly, the model-driven need for interpretability has gained popularity due to neural networks' deep versus shallow knowledge encoding and knowledges on cognitive chunks. You can find out further details in the book. I'm not going into the intricacies of all the methods, but it is important to mention those at once so that you get the overview of the different classifications and you are better informed to choose the method which might support your case. And that shall lead us ideally to AGI, artificial general intelligence, over time. Responsible AI development requires the happy Nash equilibrium between model performance and interpretability. You might be able to remember this with smiling face, where you have accurate AI or robust application and consistent performance on the one side, which most times have a trade-off with the application of interpretable AI, human collaboration, or continuous learning. But the goal of interpretability is to bridge the gap between the right to receive explanation and the right to be informed. It is about ensuring that AI systems are not only effective but also accountable, transparent, and fair. Here it's worth mentioning short and more as 5 general data which might be useful explanations for AGI as such. First is fidelity. The explanation must be a good representation of what the system actually does. Second is understandability. This includes several usability factors such as terminologies, user skills, level of abstractions, and interactions. Third is sufficiency. The AI should be able to explain functions and terminologies, and it should justify decision. Fourth is low construction overhead, that is, the explanation system should not dominate AI design cost. And fifth is efficiency. The AI should not be slowed down significantly by the explanation system. Achieving these five major general research data will help in the longer run for the AGI to be established. The importance of interpretability cannot be overstated. It's about making AI decision understandable and justifiable, ensuring that users trust and feel confident in the technology they use. When it comes to the importance of interpretability and acceptance by academics and practitioners, we must admit that not everyone will recognize the critical need for an interpretable AI system. Most people are cooks and not chefs, business persons rather than entrepreneurs, and they haven't been taught to reason from the first principles either. Data scientists often misunderstand IDL by considering the model interpretation as a placebo. In the quest for trustworthy AI, we expect stakeholders to think like us and provide a single explanations. They feel like what's said will be heard. But one motivation cannot cover all. Interestingly, Bunt et al. In 2012 asked, are explanations always important? His studies showed that black box intelligence systems are often well received despite formal explanation. This is due to a lack of clear definition of model transparency among users or the cost versus benefit of viewing an explanation. We need to ask important questions like where is it needed? For example, healthcare, criminal justice, automotive driving, or finance and security. But it's also important to see the other spectrum of where it's not needed, like in the privacy concerning situations, robustness, or already well-studied region of problem. And then we also need to ask why it is needed. Maybe it's supporting safety, science, debugging, but it's also important to see why it is not needed. It's like Jan LeCun said in 2016, considerably less important than most people think. How important is the interpretability of your taxi driver? By understanding the strength and limitations of each approach, you can make informed decisions about which method to use. In conclusion, interpretability in AI is about making models understandable and ensuring they align with the ethical and societal values. Before deploying learning models in real worlds, AI must solve the black box problem. Researchers are actively working to solve this problem. Recently, the number of research publications on the interpretability and explainability of AI has increased. IDL aims to add accountability, transparency, and fairness in AI learning model. In addition, a human-based evaluation is required for improved predictability and legal compliances. Nonetheless, it's a multifaceted challenge that requires attention from various disciplines. By working together, we can create AI that is not only powerful but also trustworthy and beneficial for all. This concludes our introductory sessions for interpretability in deep learning. And thank you for your attention. If you have any questions, feel free to ask me in the comment section or during the physical session in August. See you then. Thank you.